Well, aloha everyone. Today we're going to talk about refraction. And when we talk about refraction, we're talking about a phenomenon that light changes direction when it enters a different medium. So, take for example, and it's really related to this thing that we call Snell's Law. And Snell's Law tells us that light always takes the path of least time. That is, it takes the path between 2 points that is the fastest. So, what do I mean by that? Well, let's imagine by analogy that you're at the beach. And so here you are at the beach, and here's the lifeguard here, and here's the water out here. This is the beach. And what is the fastest way to get to a point here for the lifeguard? Well, it turns out that the fastest way is if he just runs in a straight line. That's pretty straightforward and pretty simple. But it becomes more complex if you have to deal with the water. So what if there's someone out here that needs help from the lifeguard? What is the fastest way to get there? Well, it turns out the fastest way is not to go in a straight line. Why? Because you can run faster than you can swim. In fact, pretty much everyone can run faster than they can swim. So because of that, it's going to make sense to stay on the ground longer and then swim less. Now, if I go all the way up here and go out, that's not going to work very well either, because now I've just made my path quite a bit longer as a whole. So the fastest path is going to be somewhere in between these two, where you go at an angle like this and then go at a slight angle like that. And so that way you're not in the water that much more, but the path isn't that much bigger either. Well, we can see the same thing happen to light when it encounters a different medium in which it travels slower. So here's an idea of this principle in action. I have 2 points, one right here and one right there. If I want to send a ray of light from one point to the other, the easiest way to do that is in a straight line. Something like that. And you can see here that light travels in a straight line from here to there. But what happens if light changes its medium as it goes from one to the other? Like, for instance, if it has to pass through a block of acrylic. Well, now you can see that if I just put this here, it is no longer hitting this point up here. Instead, I'm going to have to readjust this. And you can see clearly that the path that is fastest from this point to the point down there is going to be bent. Now, the mathematical form of Snell's Law, he went through the math, I'm not going to prove it to you, but we can prove that n incident is, let me write this, n incident times the sine of theta incident equals n refracted times the sine of theta refracted. So what are the pieces of this? Well, these n's are what we call the index of refraction. And they measure how much light slows down when it encounters that material. And the definition of the index of refraction is this: n is equal to c over Vm. So n is the index of refraction, c is the speed of light in a vacuum or in empty space. And Vm is the speed of light in the material. So the bigger n gets, the slower light travels in that material. N is equal to 1 for empty space, because it would be the speed of light in a vacuum over the speed of light in a vacuum. For water, it's something like 1.33. For diamond, it's up somewhere around 2.5 because diamond slows down light a whole bunch. So these n's are indices of refraction. So Ni and Nr are both the index of refraction. We have over here these thetas, and these thetas are angles. So this is what we call the incident angle. And this is what we call the refracted angle. So what do we mean by incident and refracted? Well, just remember the incident is the side where the light is traveling toward the interface, toward the place where it meets the other material. And then the refracted side is where it's traveling away from that meeting between the two materials. If you have a hard time remembering that, just remember the incident side is where the light comes in, and the refracted side is where the light goes out. So, in our little demonstration there, we had something like this. This was air, and this was, it's actually acrylic. I know that the index of refraction for air, n, is equal to pretty much 1. It's a little bit more than 1, so like 1.0002 something. But for all practical purposes, it's so close to 1 that it doesn't matter to most of us. If you're really into astronomy, you might see some little variations of that. But other than that, most of the time it doesn't matter. Acrylic over here, I don't know what the index of refraction of that is. N is equal to question mark. Let's put it down. But we can measure some things, and we can calculate it using Snell's Law. So let's make some measurements of this situation. I'm going to start out by drawing that interface. I'm going to put I'm going to know that this line is coming in to right there. And I'm going to try and draw this as best I can so that I have this line right here. Now I'm going to draw a point where this light is exiting, which happens to be right here. I can now remove this block and connect the dots. Now, I'm going to draw in the normal. The normal is going to be 90 degrees to the surface. Now we can clearly see the angles that we're going to need to measure. This is going to be theta incident, and this is going to be theta refracted. So upon measuring, theta incident is 73 degrees, and theta refracted is 40 degrees. So I measured here, I'm just going to finish drawing this diagram. So we sent a laser in like this, and then we saw it kind of divert this way. That's not a very good diagram at all. Let me see if I can draw that better. We sent light in kind of like this, and then we saw it divert kind of like that. The first thing I'm going to do is draw in the normal. The normal is an imaginary line that's 90 degrees to our surface. So something like this. And in optics, all angles are going to be measured from the normal. So we don't measure from the surface because the surface could be curved, it could be warped. So we always measure from a line that is perpendicular to the surface at any given point. So this, remember, light's traveling this way, and it's going out that way. So this is going to be theta I, theta incident. And this over here is going to be theta r, theta refracted. And when I measured this, this was 73 degrees, I think. And this side was 40 degrees. So now that we have these numbers, we can start applying Snell's Law. By the way, I will give $5 to the first person who comes to me and names their kid Snell. Or you know what? His name was Willibroyd Snell. So if you name him Willibroyd, that's an awesome name too. And I'll give $5 to the first person who comes to me and proves that they named their kid Willibroyd. All right, continuing. Let's see here. So Snell's Law, N incident sine theta incident is equal to N refracted sine theta refracted. So now I know N incident, I know theta incident, I know theta refracted. I'm looking for N refracted. So I'm going to solve for N refracted. I just need to divide by the sine of theta r. So N incident sine theta incident divided by N refracted is equal to, no, not N refracted, divided by the sine of theta refracted is equal to N refracted. Plugging in numbers, 1 was N incident times the sine of, I think it was 73 degrees? Yeah, 73 degrees, divided by the sine of theta refracted was 40 degrees. And let's see, grab my calculator. When I do this, I get 1.487. And you'll notice here that the units of degrees and degrees go away, and so there are no units here. Index of refraction is a unitless number. That means that this has an index of refraction of 1.487, which is actually fairly close to the agreed upon value for acrylic. You can look it up. Continuing here, what about the idea of total internal refraction? Well, total internal refraction is going to be based on this idea. You saw here when we drew this diagram, this angle got smaller as we went from less dense substance to more dense substance. That means the opposite will happen as well. If we reverse this diagram, if we start in the acrylic and we go to air, we can make that angle get bigger. So it turns out that as you get farther and farther and farther along, so let's say up here we have acrylic, and down here we have air. If I go from acrylic to air, so here is a ray of light going that way. I'm going to draw in the normal. The angle is going to get bigger. So if this angle is theta incident, this angle down here is going to be, so between the dotted line and here, is going to be theta refracted. And as this goes, as the light goes from acrylic to air, this is going to bend this way, because we expect this angle to be bigger, theta r. Now, eventually what's going to happen is if we make this get a little bit steeper of an angle out here, so that way we have a bigger theta incident, we're also going to have a bigger theta refracted, and it's going to get bigger faster. Theta incident here. And then theta refracted is going to go way over here. Eventually, if theta incident gets big enough, theta refracted can go right along this path, such that this is a 90-degree angle. And if we go even farther than that, then it turns out that the light can't escape this medium. And so if we have something like way over here, and we strike our surface like this, put in the normal here, instead of the light coming out of the material, it is trapped inside. Let me draw that better. That was terrible. So instead of the light coming out of the material like this, it has to bend away, but it doesn't have enough space to bend enough. What's going to happen is it's going to reflect on the inside of the material, such that this angle and this angle will be the same, theta incident, and this time theta reflected. Not sure how well I drew that, but that should be, theta reflected should be a little bit bigger probably. But that's what happens in total internal reflection. So here's an example of how we can see this happening in real life. If you look at this, don't worry about how it's entering. Look at only how the light exits. When we strike it at a fairly narrow angle, you can see that the normal would be like this, and we're very close to the normal here, and it moves away. When I strike this at a much greater angle, so if I turn it this way, now you can see that the normal is like this, and this angle is getting bigger and bigger and bigger. Eventually, as I turn this, you can see right about there, it starts to disappear entirely. And then you'll also notice that this reflection that we see going through here and bouncing off there and over here starts to get stronger and stronger until eventually, when we pass a 90 degree, so right there about, is what we call the critical angle, which causes a 90 degree refraction. So somewhere close to there, 90 degrees here, we start to get significant amounts of reflection. And then once we pass that, boom, nothing comes out, all of it is reflected. That is what we call total internal reflection. So this angle right here, the one that gives you a 90 degree refraction, is called the critical angle. Any angles that are larger, any incident angles that are larger than theta I will result in reflection. While anything that's smaller than theta I, or the critical angle as theta I, are going to result in refraction. So, how can you figure out what that critical angle is? Well, you know that the refracted ray is 90 degrees. So because of that, you can find it in any material by saying this. The sine of theta incident n incident times the sine of theta incident equals n refracted sine theta refracted. If we know that theta refracted is going to be 90 degrees, we can solve this for theta incident. So I'm going to divide by n incident. I'm going to get sine theta I equals n refracted times the sine of theta refracted divided by n incident. Then we're going to take an inverse sine. So the theta incident is going to be equal to the inverse sine, or the arc sine, of n refracted sine theta refracted divided by n incident. For our acrylic here, we can calculate the critical angle. So I'm going to plug in theta incident is equal to sine to the -1 of n refracted. Well, that is, this time we're going from acrylic to air. So this is the incident side, and this is the refracted side. So if we're doing that, we're going to have the n refracted be 1 times the sine of 90 degrees divided by n incident we found earlier was 1.487. So this should be 1.487. Plug that into the calculator. And I get 42 let's call that 259, let's call that 26 degrees. So if the angle is anything greater than 42.26 degrees, it will reflect. If it's less than 42.26 degrees, it will refract. So that's really all there is to it as far as refraction goes. Mahalo for watching. and see you next time.